All right, strap in everyone. Today we're taking a deep dive, you guessed it, into the world of neutrinos.
Tiny particles.
Yeah. Almost massless, zipping around all over the place.
Messengers from the universe.
And we're talking about some pretty intense messengers too, right? Supernovae, black holes, the really big stuff.
And the craziest part is scientists at the KM3NeT Neutrino Observatory just detected the most energetic one ever. Led by Jörg-Owe.
That's right. We'll talk more about that later.
I actually wrote the paper we're diving into today.
So think about it this way.
Yeah.
It's a tiny, almost massless particle.
Right.
Traveling from a distant galaxy.
Billions of light years.
Carrying an unimaginable amount of energy.
More than anything we can create here on Earth.
That's what we're talking about today.
It's really incredible.
Okay, so for anyone out there who maybe didn't ace their physics class.
We've all been there.
Let's take a step back.
Yeah.
What exactly are neutrinos?
Right, so...
And why should we even care about them?
Well, think of them like cosmic messengers.
Okay.
Born from the most violent and energetic processes in the universe.
So like the Big Bang?
Well, not quite the Big Bang itself.
Okay.
But definitely things like supernovae.
Those giant exploding stars.
Exactly. And these neutrinos, they travel across vast distances.
Like how vast are we talking?
Billions of light years.
Wow.
And get this, they barely interact with anything.
Anything.
They can pass right through planets, stars, almost like they're not even there.
So they're like ghost particles.
Pretty much.
That's wild.
It's like they have a backstage pass to the universe's craziest events.
They're witnessing things that light and other particles just can't show us.
Exactly. And that's what makes them so valuable to scientists.
Because they're like little spies, bringing us information from places we could never reach.
Right. By studying neutrinos, we can get a glimpse into events that are hidden from other forms of observation.
Events that could, like rewrite our understanding of the universe.
Exactly.
Okay, that's pretty cool.
And that brings us back to this record-breaking neutrino.
The big one.
The one they found using KM3NeT.
You know, it's funny, when I think of a telescope, I think of something like up on a mountain.
Right, like Hubble.
Exactly.
Yeah.
But this thing, it's not your average telescope.
Not even close.
In fact, it's like submerged over 2 miles deep in the Mediterranean Sea.
It is, yeah.
What's up with that?
Well, it's all about filtering out the noise. You see, neutrinos are notoriously difficult to detect.
Ah, because they barely interact with matter.
Exactly.
Okay, that makes sense.
So to actually catch them, you have to get creative.
Okay.
And by building a detector deep underwater, they can shield it from all the other particles bombarding Earth, cosmic rays and things,
right,
making it easier to spot the faint signals of these elusive neutrinos.
So they built this massive structure.
It's huge.
In the crushing depths of the ocean.
3,500 meters down.
Just to catch these tiny, tiny particles. That's some serious dedication.
It is, but the things we do for science, right?
Absolutely.
Yeah.
But how did they actually detect this record breaker?
Well, it wasn't like it rang a bell or anything.
Oh, too bad.
But they used a pretty cool principle called Cherenkov radiation.
Cherenkov radiation.
It's a mouthful. I know. It is. Basically, when a neutrino, a very high energy neutrino, interacts with the water molecules in the detector, it creates a faint flash of light.
Okay.
And it's that flash of light that lets us know, hey, something extraordinary just happened here.
So it's like a little beacon signaling, hey, look at me.
You got it.
And this time the beacon was brighter than they'd ever seen before, right?
Brighter than ever.
We're talking about a neutrino with an energy of 220 peta-electron volts?
Yeah.
To be honest with you, I have no idea what that means.
It's a lot of energy, let's put it that way.
But it sounds impressive.
Oh, it is. Let's put it this way. The Large Hadron Collider.
That big thing in Switzerland.
Exactly. Our most powerful particle accelerator on Earth.
Okay.
It can reach about 13 tera-electron volts, which is already a lot.
That's huge.
But this neutrino was packing over 16,000 times that amount of energy.
No way.
Yeah, it's mind-boggling.
Hold on, let me do the math. Carry the one. Okay, yeah, that's a lot of energy.
It is.
And it means this neutrino, this little guy, must have come from a truly mind-blowing event.
Some crazy cosmic event, that's for sure.
But what could possibly create that much power?
Now that's the million-dollar question.
It is.
Right now, scientists are looking at all sorts of possibilities.
All right, give me the rundown.
Okay, we're talking supernovae, of course.
It's exploding stars.
Active galactic nuclei, AGN for short.
Those are the supermassive black holes, right?
You got it. They're at the centers of galaxies, just gobbling up matter.
And spitting out jets of radiation.
Exactly.
Okay, so black holes, supernovae.
Maybe even collisions between supermassive black holes.
Whoa, hold on. Black holes colliding.
It's slot to happen.
That's intense.
Each of these events is capable of unleashing unimaginable amounts of energy.
And some of that energy is carried by neutrinos.
And those neutrinos can travel for billions of years.
Giving us a glimpse into these events.
Exactly.
So this single neutrino detection is basically challenging everything we thought we knew about these cosmic events.
It's definitely shaking things up, that's for sure.
Because scientists have all these models and theories.
You do, yeah.
But this neutrino is so far outside the expected energy range.
It really is.
It's like it's breaking the rules.
It's forcing us to reevaluate our assumptions, that's for sure.
Wow. Talk about rocking the boat.
Right.
But wait a minute. Haven't I heard of other neutrino observatories?
You have. There are a few others out there.
Like IceCube?
Yeah, IceCube down in Antarctica.
That's right. They're looking for neutrinos too, right?
They are, and they've found some pretty incredible things too.
But have they seen anything like this?
And that's where things get even more interesting.
No.
Because while IceCube has also detected high-energy neutrinos, their findings don't quite match up with what KM3NeT has observed.
Really?
Yeah, and this is where the real head-scratching begins.
So are we talking about different types of neutrinos?
Possibly.
Maybe different sources altogether.
That's another possibility.
So maybe there's more to these little particles than we thought?
That's what scientists are trying to figure out.
Okay, now I'm really intrigued.
It's a puzzle, isn't it?
It is.
Could there be a whole family of neutrinos we haven't even discovered yet?
A whole family?
That's what some scientists are wondering.
Wow.
And are there cosmic events so powerful, so strange?
Like what?
We don't even know yet.
That we haven't even begun to imagine them.
Exactly.
Okay, my mind is officially blown.
It happens.
So this isn't just about a single record-breaking neutrino, is it?
Nope.
It's about opening a window into a whole new realm of cosmic possibilities.
Precisely. This discovery, thanks to Schneppet and his team,
Right.
It's just the tip of the iceberg.
We're just getting started.
Exactly. We're on the verge of a new era in astronomy, where neutrinos are our guides to the universe's greatest mysteries.
This is why I love these deep dives.
Me too.
1 minute we're talking about tiny particles.
Yeah.
The next minute we're pondering the fate of the universe.
It's all connected.
But before we get too carried away,
Okay.
let's take a closer look at KM3NeT itself.
Right. The observatory.
What makes this thing so special?
Well, it's unique in a lot of ways.
And what can it tell us that other telescopes can't?
Oh, so much.
All right, I'm ready to learn more.
Let's dive in. Well, for starters, it's all about location.
Location.
Exactly. KM3NeT is strategically positioned in the Mediterranean Sea,
Okay.
giving it a unique perspective on the cosmos, compared to other observatories.
Right, like IceCube.
Exactly. IceCube's at the South Pole.
So
KM3NeT's in the Mediterranean.
they're looking at different parts of the sky,
It's like having eyes on opposite sides of our planet.
each capturing a different slice of the neutrino sky.
You got it.
So by combining data from these different locations,
Uh-huh.
we get a more complete picture of what's out there.
Exactly. And KM3NeT's not just looking in one direction.
Oh.
It actually has two main components.
Okay.
RCA and ORCA.
Catchy names.
Yeah, scientists love their acronyms.
So what's the difference?
Well, RCA is designed to detect those ultra-high energy neutrinos.
Like the record breaker we've been talking about.
Exactly.
Yeah.
While ORCA focuses on lower energy neutrinos
Well,
coming
how's
from sources within our own galaxy.
Oh, I see.
So it's like having two telescopes in one.
Each tuned to a different frequency.
You got it. A different frequency of the neutrino spectrum.
This is pretty cool.
And this dual capability is crucial
Why is that?
because it allows scientists to study a wider range of cosmic phenomena.
Okay, so we can learn about both the really intense stuff
The high energy event?
and things happening closer to home.
Exactly.
Makes sense.
We can compare and contrast the information from both RCA and ORCA
To get a better overall understanding.
to piece together a more comprehensive understanding of neutrino sources and behavior.
This is making me think
Yep.
about those discrepancies between KM3NeT and IceCube.
Uh-huh.
Could they maybe point to something, I don't know, fundamentally new about neutrinos?
Ooh, that's a great question.
Like, what if they're not all created equal?
You're getting into some really cutting-edge territory now.
Am I?
You are. Because some physicists have been theorizing that there might be something called sterile neutrinos.
It's sterile neutrino?
It's a hypothetical type of neutrino that interacts even more weakly with matter.
Even more weakly?
Than the ones we're already familiar with.
So these are like ghost particles of ghost particles?
Pretty much.
Okay, now that's just crazy.
It is a mind-bending concept.
But that's what I love about science.
Right.
The more we learn, the more we realize how much we don't know.
Exactly.
And this mystery surrounding sterile neutrinos, if they're even real,
it's a big
could completely change our understanding of particle physics.
And the universe as a whole, potentially.
It's amazing to think about.
Isn't it?
These tiny, invisible particles traveling billions of light years
across the vastness of space
could hold the key to unlocking some of the biggest secrets out there.
They really could.
And to think, KM3NeT is still under construction.
It's not even finished yet.
Imagine what we'll learn when it's fully operational.
It's going to be incredible the amount of data we'll be able to collect.
It's like we've only dipped our toes into the neutrino ocean.
It is.
And there's a whole universe of knowledge waiting to be discovered.
I love that analogy, the neutrino ocean.
It's vast, mysterious.
And full of potential.
Exactly. And these discoveries, they go far beyond just understanding neutrinos themselves.
Right, it's bigger than that.
By studying these cosmic messengers, we can learn about galaxy formation, black holes, cosmic rays.
All sorts of things.
So we've established a few things.
Yeah.
Neutrinos are awesome. KM3NeT is a game changer.
Absolutely.
And there's still a lot we don't know.
A whole lot.
But what does this all mean for the average person?
Yeah, for big question.
You know, the person who isn't a physicist, who maybe doesn't spend their days thinking about neutrinos and black holes.
Right.
Why should they care about these discoveries?
Well, I think at its core, this is about pushing the boundaries of human knowledge. Every time we uncover a new secret about the universe, we expand our understanding of our place within it.
So it's not just about the science itself.
It's about understanding ourselves.
Our connection to the cosmos.
Exactly. And it's like adding another layer to our cosmic map.
Making the unknown a little less daunting.
I like that. It's a good way to think about it.
And who knows, maybe these discoveries will lead to new technologies.
Absolutely. That's always a possibility.
New ways of thinking, new art forms even.
You never know where inspiration will come from.
That's true.
So yeah, I think everyone should care about these discoveries, even if they don't fully understand the science behind them.
Because it's about the bigger picture.
It is. It's about our place in the universe and pushing the limits of what we know.
I like that.
And speaking of pushing limits, given all the unknowns, the challenges of detecting these neutrinos.
Right, it's not easy.
The vastness of the universe.
How do scientists even know where to start?
It's a good question.
What do they focus on?
Well, it's a combination of intuition, experience, a lot of trial and error, honestly.
Really?
Yeah. They're constantly refining their models, developing new techniques, collaborating with each other.
So it's a team effort.
It really is a global effort.
Trying to narrow down the possibilities.
It's like putting together a giant cosmic jigsaw puzzle.
One tiny piece at a time.
Exactly.
And this record-breaking neutrino, thanks to Schnepped's team.
Right, they found an important piece.
That's a big piece of the puzzle.
It is. And speaking of pieces, I think there's one part of this neutrino story we haven't touched on yet.
What's that?
The sources themselves.
Ah, yes. We've talked about how much energy this neutrino had.
A lot.
But we haven't really discussed where it came from.
And that's where things get really interesting.
All right, I'm ready to hear about these potential neutrino factories.
They're pretty wild. Get ready. All right, so picture this.
I'm picturing it.
Events so powerful.
Yeah.
They can launch these tiny particles, neutrinos.
Right.
Across billions of light years.
It's hard to even imagine.
It is, and they're carrying more energy than anything we can create here on Earth.
It's mind-boggling.
It really is, and the prime suspects.
Okay, the usual suspects.
They're some of the most extreme phenomena in the universe.
Lay it on me.
So first up, we've got supernovae.
Supernovae, those are...
the spectacular explosions that mark the death of massive stars.
Okay, yeah, I remember learning about those, like giant cosmic fireworks.
Exactly. And they release a tremendous amount of energy.
Enough to, what, create new elements?
More than enough. They forge heavy elements and fling them across the cosmos.
Wow.
And some of that energy, you guessed it, is carried by neutrinos.
Neutrinos always there.
And get this. They escape the exploding star before the light even reaches us.
So we're getting a sneak peek.
We are. Neutrinos are giving us a glimpse into these cataclysmic events before we can even see them with telescopes.
That's incredible.
It is. And then we've got another contender.
Okay.
Active galactic nuclei.
Active galactic nuclei.
AGN for short.
Okay, AGN.
Which are basically...
Let me guess. Black holes.
You got it. Supermassive black holes at the centers of galaxies actively devouring matter.
And spewing out jets of radiation and particles.
Exactly.
Black holes are already mind-blowing on their own.
They are.
But now you're telling me they can launch these high-energy neutrinos too?
Think of it like this. As matter swirls around a black hole, it gets superheated and compressed.
Right, makes sense.
Creating this chaotic environment where neutrinos can be produced like crazy.
Right.
And some of those neutrinos, they get caught in the black hole's powerful jets.
Those jets we were talking about.
And blasted out into space at nearly the speed of light.
It's like a cosmic particle accelerator.
It is.
Powered by a black hole.
Exactly.
But wait, you said there were even more extreme possibilities.
We're just getting started. Some scientists believe that even more powerful events, things like collisions between supermassive black holes.
Wait, black holes can collide?
It's thought to happen, yeah.
That's insane.
It is.
Okay, so black hole collision.
Or the decay of hypothetical particles called WIMPs.
WIMPs? What are WIMPs?
WIMP stands for weakly interacting massive particles.
So they're weak.
Well, they interact very weakly with matter.
Okay.
And they're a leading candidate for dark matter.
Dark matter, that mysterious stuff that makes up, what, like 80% of the universe?
Something like that, yeah.
So we're talking about potential connections between neutrinos, black holes, dark matter.
It's all connected.
This is getting really deep.
And that's what makes this field so exciting. With each new discovery, we're peeling back another layer of the cosmic onion, revealing deeper connections and more profound mysteries.
I like that, the cosmic onion.
It's a good analogy.
So many layers to uncover.
And who knows what we'll find at the center.
Okay, so we've got a whole cast of cosmic characters here.
We do!
Who could be responsible for this record-breaking neutrino.
But the question is, how do we actually pinpoint this source?
Right, it's not like we can just follow the neutrino back to its home.
If only it were that easy.
It's more like trying to solve a cosmic crime scene.
Exactly, with only a few clues.
And neutrinos are just one piece of the evidence.
Exactly. Scientists use a combination of techniques.
Like what?
They compare the neutrino's arrival direction with known astronomical objects.
So they're looking for a match?
They analyze its energy spectrum and look for correlations with other types of observations, like gamma rays or cosmic rays.
So it's a lot of detective work.
It really is.
But with each new neutrino detection,
especially one as remarkable as this record breaker,
we get closer to understanding the big picture.
The grand symphony of the universe.
It's beautifully put.
It's amazing to think that these tiny particles, so difficult to detect, can tell us so much about the universe's most powerful and mysterious events.
It really is. It's humbling.
And remember, we're only just scratching the surface.
Always scratching the surface.
KM3NeT is still under construction, and other neutrino observatories around the world are constantly gathering more data.
So there's more to come.
A lot more. And as our understanding of neutrinos grows, who knows what incredible discoveries await us in the years to come.
This has been an incredible deep dive.
It has.
From the depths of the Mediterranean Sea to the farthest reaches of the cosmos.
We've covered a lot of ground.
We've explored the amazing world of neutrinos and the secrets they hold about the universe.
And it all started with a single, incredibly energetic particle.
Detected by the amazing team at the KM3NeT Neutrino Observatory.
Led by the brilliant Jörg-Owe.
It's a testament to human curiosity, ingenuity, and the never-ending quest to understand our place in the universe.
And that quest continues.
It does. So the next time you look up at the night sky, remember those tiny neutrinos?
Zipping through the cosmos.
Carrying whispers of cosmic events that defy imagination.
Who knows what secrets they'll reveal next?
That's a beautiful thought to end on.
Thanks for joining us.
Thanks for being here, and we'll see you next time for another adventure into the fascinating world of science and discovery.